Imagine how it would be to control a robot with your own body, if you could just move your hand and at the same time teleoperate a remote device. And not just a common industrial robot like the ones you see every day, but a robot that can grow, modify its shape based on the environment, and reach for targets in a complex scenario. To do so, you would have to match all the differences between your body and this growing robot's kinematics. This is what our paper is about. I am Fabio Stroppa from Stanford University, and this is a human interface for teleoperated object manipulation with a soft-growing robot. Soft and continuum robots have useful features that are advantageous in applications requiring delicate interaction or adaptation to unknown environments. A subset of soft robots have an additional feature that makes operations in confined environments easier, the ability to extend or grow. By extending and shortening in length, these systems can move their tip through cluttered environments without being restricted by body parts that may collide with obstacles, such as the elbows on a typical robotic arm. For this reason, growth can be especially beneficial in manipulation tasks. We call this degree of freedom eversion. Designing control for eversion is challenging, since kinematic models for soft robots are not yet well defined. Soft robotic systems usually rely on humans to close the loop. However, the differences between robots and humans in terms of degrees of freedom makes it difficult to find appropriate control interfaces. We propose an interface that allows humans to control the robot simply by using their arm. The gestures of the operator are tracked by a motion capture system and then mapped to the kinematics of the robot for easy and intuitive teleoperation in a manipulation task. We call it the body interface. During this presentation, I will illustrate the specifics of our soft-growing robot, the details of the body interface, and finally, I will discuss the experiment we carried out to test manipulation. Let's start from the robot. We built a soft-growing robot specifically for manipulation tasks. It can grow, retract, and steer in 3 dimensions while carrying a payload. In this particular configuration, the robot's base is attached to the ceiling, such that the robot grows in favor of gravity to reach the targets from the top, kind of like an arcade claw machine. When growing, the internal pressure within the container pulls new material to add at the tip. When retracting, a DC motor embedded within the container pulls the material back. The robot is made of polyurethane, and it can grow up to 1.5 meters with a diameter of 10 centimeters. The robot is steered by external cables. 3 gear motors shorten the cables in the direction we want the robot to bend. Lastly, the gripper is driven by 2 servo motors, one for rotation and the other one for grasping. This red attachment moves with the tip when the robot grows. It is composed of 2 parts, one inside the robot and one outside, connected to each other by magnets. The material moves through the center of the inner part and then slides in between the magnet pairs, keeping the mechanism centered as the robot grows. Now, let's talk about the teleoperation interface. This picture shows an operator wearing the body interface. For presentation purposes, the operator is shown really close to the robot, but in a real case, the users will be at least 1 meter away from it, such that the cameras can see the markers. The body interface is composed of 7 markers. The 3 markers on the chest are used to define a reference system, such that the operators are not constrained in a specific position and are free to face the robot as they prefer. The 4 markers on the arm are the ones that actually control the robot. 2 markers are on the elbow and 2 are on the wrist, so that the angle between these segments can be used to rotate the gripper. Controlling the robot is very intuitive. Moving the arm down will make the robot grow, and bringing it back up will make it retract. The same goes for steering. Left and right movements will make the robot mirror the operator's gestures, as if it was their own limb. We use the pick-and-place task to test the system, which includes the body interface and a soft robot. The experiment consisted in picking up a block, which is placed on a pillar underneath the robot's base, and then moving it onto a designated target. 3 smaller pillars of different heights define the possible targets. The tallest on the left, a slightly smaller on the right, and the smallest in front of the starting pillar. 12 participants were randomly and equally divided to explore all 6 combinations of target ordering, and they were asked to repeat each trial 5 times for each target, for a total of 15 repetitions for each participant. This is a footage we took while running the experiment. As you can see, the robot responds promptly to the movements of the operator. With this experiment, we evaluated the system usability in terms of accuracy, timing, and workload. The accuracy of the placement was evaluated by measuring the distance between the center of the block and the center of the target at the end of each trial. In cases where the block did not reach the target pillar at all, the trial was marked as a failure. This failure rate serves as an additional indication for accuracy. When this happened, the trial was discarded and we asked the participant to repeat it. To evaluate timing, we measured the time required to complete a single trial, the time required to grasp the object, and the time required to place the object. For these last two, we also considered the duration of the task minus the time spent everting the robot, since this may be more indicative of the task difficulty and allow comparison of targets with different amounts of growing time. To measure workload, we used the standard NASA Task Load Index, a subjective assessment specifically structured to rate the perceived workload. Participants were asked questions about mental load, temporal load, effort, and frustration scale. Let's discuss the results. This histogram shows the target placement error over all trials, summarizing all participants and all targets. You will notice that most of the trials are concentrated here, indicating that most of the participants were performing the task with an error lower than 2 cm. Many trials had error below 5 mm, and 3 of them achieved an error less than 2 mm. This shows that the operator can achieve accurate performance when controlling the soft robot with our interface. The histogram also shows the low failure rate. Only 5 trials were discarded against 180 successful performances, which translates to a 3% failure rate and 97% of successful placing. This plot shows the commanded location of placement versus the error in the 2D space as seen from above. Note that this is the location of the operator's hand, not the location of the robot. The color of the dots indicates the placement error for that trial. We can notice that some high error placements occurred close to the center of the clusters, and some low error placements occurred well outside. The high error dots can be explained by the quality of the initial grasp, which would cause the block to roll or move significantly after being released. The low error spots, on the other hand, show where the operators dropped the block from a height instead of growing the robot as far and placing it safely. This strategy required a larger steering command to reach the same location vertically over the target, putting those trials outside the cluster. This next plot shows the timing. The grasping phase was consistent across targets, whereas the placing phase required more time. This is true especially for target 3, which was the furthest from the starting position of the cube and required more growing time. However, if we do not consider the time spent during eversion, there are non-noticeable differences between grasping and placing. This indicates that the difference in time was spent on growing the robot and does not indicate increased difficulty. Therefore, steering the robot was equally easy at all ends. Finally, the results of the NASA TLX showed an average workload value of 68% among all the participants, which indicates that the task was challenging but not overly demanding. The participants indicated that the grasping phase was slightly more difficult than the placing. It was easy to hit the block with the gripper when trying to align the robot well, especially after overshooting in growth. In conclusion, we propose a human-centered interface based on motion tracking to teleoperate a soft-growing robot in a pick-and-place manipulation task. Our interface has shown promising results in terms of performance, proving to be intuitive and easy to use. In the future, we hope to integrate shared autonomy strategies in our system to achieve even better performances. Thanks for watching, and for more information, please visit vinerobots.org.